Alright, hello class. In this video we're going to be talking about the mean value theorem and some of the things that are related to the mean value theorem. So what the mean value theorem is, it's kind of like the intermediate value theorem that we have for continuous functions. It's just a similar result that we have with differentiable functions. If functions are both differentiable and continuous. Okay, so the beginning of this is really Rolle's theorem. So we're going to start by talking about Rolle's theorem, what that gives us, and then move on to the mean value theorem. Alright, so let's start with Rolle's theorem. Rolle's theorem basically says we're going to suppose that f is continuous on the closed interval a to b, and differentiable on the open interval a to b. So basically just differentiable on the interior. If f of a is equal to f of b, then there exists a c in a to b such that f prime of c is equal to 0. Alright, so what this is basically saying is that if a function is continuous and differentiable, and it ever has a repeated y value, then it must have a critical point. Okay? Or to put it another way, if f ever repeats a y value, then it must have a critical point in between. So what this is saying is that if you have a function that is both continuous and differentiable from some value a to b, and it's on a closed interval, and it has the same exact y value, right? F of a and f of b are the same, then the only way that can happen is if somewhere in between these two there's a place where the derivative is equal to 0. Right, so given a scenario like this, there's actually no way we can draw a function from this point to this point without there being a turning point, or it's just flat. Okay, so we could say increase from this point, and then if we want to get back to here, we have to go back down, right? We have to add in a turning point, which gives us, of course, a place where the derivative is equal to 0. So that would be RC. Okay? But it's not the only way to go about it. Like, there are countless ways that we could go from, say, this point to this point, and in all of them we get at least one, but in some cases more than one, place where we get a horizontal tangent line where the derivative is equal to 0. Okay? Now, you might be thinking, well, what if we did something like this instead? Well, then the function would not be differentiable, right? So that's part of the hypothesis, is that the function has to be differentiable between a and b. Okay, so it can't have, say, a sharp turn like this. It can't have a jump, right? It can't do something like that because it's also continuous on a to b. Okay, so we either have to satisfy all these requirements, we have to either have some turning points, some nice smooth turning points, or the function is just a constant between them, right? It might just be a flat constant. Okay? And there, its derivative would be 0 everywhere. But other than that case, no matter how we draw the function, we're going to get points, at least one point, okay, where the derivative is equal to 0, and in other words, that means we have at least one critical point in between a and b. So that's what Rolle's theorem is telling us, right? That, okay, if we ever repeat y values, okay, then somewhere in between there, the function has to have a turning point, and it's got to be a smooth one if the function is, well, smooth. All right, so this is the kind of question you might be asked about Rolle's theorem. Is that we, given, a function and an interval, we want to determine if Rolle's theorem applies, and if so, we want to then find the points guaranteed to exist by it. Okay, so for example, let's say f of x is equal to x times x minus 1 all squared, and we want to determine if Rolle's theorem applies on this interval, say 0 to 1. Well, first of all, Rolle's theorem requires that the function be continuous and differentiable on the interval. So this function is definitely, if we FOILed it out and multiplied it through, this is just a polynomial. So it's going to be differentiable and continuous everywhere. So that part's fine. Then if we plug in, say 0, we'll get 0 out. And if we plug in 1, we also get 0 out. So yes, the first answer to the first question is yes, Rolle's theorem applies. Now we want to find the points guaranteed to exist. So what Rolle's theorem says is there must, okay, so there exists as c, or an x equals c, in 0 to 1, or f prime of c is equal to 0. In other words, there's a critical point in this interval. And that is the important part, that, oh, not only do we know that there's a, it's satisfying Rolle's theorem, what Rolle's theorem gives us is that there's a critical point. So this is actually a really nice way to tell if you have critical points before you even go to look for them. Okay, so that's the nice thing about Rolle's theorem for us, is that it gives us a condition to check for before we even start looking for critical points, because how do we find critical points? Well, we find the derivative and we set it equal to 0. So I'm going to take the derivative, f prime of x. The way it's set up here, I'm going to go ahead and do a product rule. It'll be 1 times the second function left alone, plus the first function left alone times the derivative of the second, which will be 2, times x minus 1, times the derivative of the inside, which will be 1. Okay, so this is x minus 1 squared plus 2x times x minus 1. And we're going to set this equal to 0 and solve. Okay, and to do that, I always recommend factoring if you can. We can factor out an x minus 1. So this will be x minus 1 all times x minus 1 plus a 2x left over. Okay, and this whole thing's equal to 0. So we get x minus 1. I could probably start dropping those now. And this will end up being 3x minus 1 equals 0. Okay, so x is equal to 1, or in this case, 1/3. Okay, so the 1 we don't need to really worry about. It's the 3. So the c is 1/3. So 1/3 is the critical point guaranteed to exist in between 0 and 1 by Rolle's theorem. Okay? All right, let's look at another example. Okay, so same question, but we're looking at the function 1 minus x to the 2/3 on the interval -1 to 1. Now, we need to be careful here because this function is continuous, but it may not be differentiable. Okay, so f is continuous. Right, because with fractional exponents, you need to worry about if you have an even denominator, but we have an odd denominator, so we can plug in negatives and positives and 0, and all that's fine. So this is continuous, And it does satisfy another part of Rolle's theorem, which is that f of -1 is going to be 1 minus -1 to the 2/3. So when you square the -1, it becomes 1. And then when you take the cubed root of 1, it becomes 1. So this is 0. And then, of course, f of 1 is 1 minus 1 to the 2/3, which is also 0. So it satisfies all these things about Rolle's theorem, except here's what we need to be careful about. Is it differentiable on -1 to 1? Okay? And a quick way to see that is if we take f prime of x, and it's just going to be a power rule here. It'll be -2/3 x to the 2/3 minus 3/3, which will be -1/3. So this is -2/3 times 1 over x to the 1/3, and f prime is undefined at 0. All right, so that means f is not differentiable on -1 to 1. At 0, it's not differentiable, right? So Rolle's theorem is not applicable here, right? It does not work. So Rolle's theorem is not applicable. Okay? And at the same time, there's not going to be a place where f prime equals 0 because, well, there's no way to get this to equal 0. All right? So we won't ever get that result. All right, real quick, here's another similar example. It's almost the same. If our function is 1 minus the absolute value of x, well, we've described that the absolute value of x is not differentiable, okay, and it's not differentiable at 0. So absolute value of x is not, I'm just going to put diffable, okay, at x equals 0. So that's really the only thing I need to see right off the bat. If I see that the function is not differentiable in this interval, then Rolle's theorem does not apply. Okay, so right there, we're done. All right, because we know the absolute value sort of makes a v. All right, so once again, for this function, let's determine if Rolle's theorem applies, and if so, let's find the points guaranteed to exist. So if f of x equals x cubed minus x squared minus 5x minus 3 on the interval -1 to 3, we first want to determine if Rolle's theorem applies. So it's a polynomial. So polynomial gets the continuity and the differentiability without really having to think much about it. Okay, there's nothing that's going to cause it to blow up or mess up, and it's differentiable everywhere. Okay, the next thing we need to note is we need to figure out if it matches on the endpoints here of our interval. So we're going to check f of -1 and f of 3. Okay, and when you plug both of these in, you get 0. You get 0 at -1 and you get 0 at 3. So Rolle's theorem does apply. So that means there's at least one critical point in the open interval -1 to 3. Okay, so let's find it. Okay, to find the critical point, of course, we're going to start by finding the derivative. So the derivative is 3x squared minus 2x minus 5. And we're going to set that equal to 0 and solve. Right, and this is a situation where if it factors, we're going to need to use the AC method. So I'm going to take 3 times -5 and see if I can find two factors of -15. That would sum up to be -2, and actually it looks like it'd be 3 and -5, exactly the two that we have. And using the AC method, of course, we rewrite that middle term using these two coefficients. So it's going to be 3x squared plus 3x minus 5x minus 5 equals 0. And from the first group, so remember we split these into groups. In the first group, we can take out a 3x to get x plus 1. And in the second group, we can take out a -5. also be left with x plus 1. That's how it should always work. If it doesn't, then you can't factor, at least not this way. Okay, and so now we can take out the x plus 1. So we get x plus 1 times 3x minus 5 equals 0. Right, so x is either -1 or 5/3. All right, and of course, just this 5/3 is the critical point that's guaranteed to exist in this interval -1 to 3 open. All right, so this actually brings us to the mean value theorem. So the mean value theorem is just an extension of Rolle's theorem, or you can think of Rolle's theorem as a very special case of the mean value theorem. What the mean value theorem says is that if f of x is continuous on a to b closed and differentiable on a to b open, so same beginning condition, then there is at least one point C in a to b open such that f prime of c is equal to f of b minus f of a all over b minus a. All right, so this is a generalization, right? It generalizes the Rolle's theorem, okay, and makes it a little more useful. Notice we don't need that extra condition that f of a is equal to f of b. But what does this actually say? Well, remember, this is the average rate of change over the interval a to b, and this is the instantaneous rate of change at a point within a to b. Okay, so what the mean value theorem says is that if a function is continuous and differentiable, okay, then there's a point in the interval where the derivative, or the instantaneous rate of change, is going to equal the average rate of change. Okay, in other words, write it out in words here. There's a point where the instantaneous rate of change equals the average rate of change. And to show in a graph what we mean by that, if this is what the function looks like, okay, and this is a, and this is b, okay, the average rate of change is going to be the slope of this line right here. All right, this is the average rate of change. Okay, but notice how this has been drawn is there are two places where the tangent line lines up with the average rate of change. Right, so here the slope is f prime. Here the slope is f prime. So this would be, say, one of our c's. This could be a c1 and this could be a c2. Now, why it's a generalization of Rolle's theorem, or you could think of why is Rolle's theorem a special case of this, is because if f of a is equal to f of b, right, then the average rate of change on the interval is 0. Right, so when they're equal, the average rate of change is equal to 0, and then there's a place where f prime equals 0. Okay, so this just lets it apply to pretty much any situation where the function is, of course, differentiable and continuous. Okay, so that's what the mean value theorem is saying. It's basically, imagine it's Rolle's theorem, but we can like tilt it in any direction we want. I think this one benefits from a couple more examples, all right? But just keep in mind, it's the same idea, except instead of just guaranteeing there's a point where the derivative is 0, we can guarantee a point where the derivative matches the average rate of change. And we'll show an example in a little bit of why that's useful, like, you know, what, how that can be used in the real world. Okay, so let's take a look at some examples, and then we'll talk about that. Okay, like before, we're going to determine if the mean value theorem applies. less things to check now, but we still need to check if the function is continuous and differentiable. And if so, we want to find the point or points guaranteed to exist by the mean value theorem. All right, to give an example, let's say f of x is equal to x cubed minus 2x squared on the interval 0 to 1. This is a polynomial, so it's continuous and differentiable, so that part's fine, and that's all we need for the mean value theorem. So the mean value theorem can be applied because f is continuous and differentiable. All right, now, so since the mean value theorem applies, that means there's a point where the instantaneous rate of change, the IRC, equals the average rate of change, ARC. So first, let's find the average rate of change on the interval 0 to 1. So the average rate of change from, say, 0 to 1, okay, is going to be, well, remember that's f of 1 minus f of 0 all over 1 minus 0. Okay, so when we plug in the 1, that's going to be 1 cubed minus 2 times 1 squared. Right? Then minus, well, plugging in 0, we just get 0. And this will be all over 1, so we can basically just sort of ignore that. Okay. Then this comes out to just be 1 minus 2, which is negative 1. Okay, so that's the average rate of change over the interval, is that there is, the average rate of change is negative 1. So the mean value theorem says, so it says that there's a point C in 0 to 1 open where f prime of C is equal to negative 1. So in other words, there's a point where the derivative is equal to negative 1, and then there's at least one of them. So let's find that point. So we need to find the derivative, and it's just like finding the critical points, except now instead of setting it equal to 0, we're setting it equal to negative 1. So the derivative is going to be 3x squared minus 4x. And now we're setting that equal to negative 1 instead. All right, so this does change things a bit because now we're solving this equation. 3x squared minus 4x plus 1 equals 0. All right, and once again, we'll use the AC method since there's not just a 1 in front of the x squared. And we're going to look for factors of 3. That will sum up to negative 4, and that will be negative 1 and negative 3. Okay, so rewriting the middle term as, let's put the 3's together. So we'll have negative 3x minus 1x plus 1 equals 0. And so now we can take the 3x out of this group to get 3x times x minus 1. And then we're going to want to take a negative 1 out of this to get the signs to match. So it'll be negative 1 times x minus 1. Okay, so now we can factor out the x minus 1 to get x minus 1 times 3x minus 1 equals 0. So x is either equal to 1 or x is equal to 1/3. So 1/3 is the C value that is guaranteed to be in 0 to 1. Notice we have another, but that's the endpoint, right? So we're not really looking for that. All right, next up, let's look at a same question, different function. Let's say now our function is 1 over x minus 1 all squared on 0 to 2. Now, we first want to know, is this function going to let the mean value theorem apply? I'm going to say no, because f is not continuous at 1, right? F of 1 is undefined. Right? So f of 1 is undefined, so f is not continuous at 1, and is thus not continuous on 0 to 2, closed or open, or anything containing 1, so the mean value theorem does not apply. Okay, so we don't need to worry about it. All right, so the nice thing about things like this is if you just see automatically that they're not continuous or differentiable, there's nothing left to do. So this can help later on if we're looking for critical points, say with Rolle's theorem or doing other things. If the function's not differentiable or continuous where you're looking, then you might not even need to bother looking for those points. All right, so next up, let's look at the function. Let's say the natural log of 3x on the interval 1 to e. Now, natural log is continuous and differentiable on 0 to infinity, not including 0, but that's fine. So the mean value theorem does apply here. So I'll just say MVT applies. All right, so that means there definitely does exist a point where the instantaneous rate of change equals the average rate of change. Or to put it another way, there's a point where f prime equals the average rate of change. So let's find the average rate of change of our function on 1 to e. Okay, so the average rate of change, well, that's going to be f of e minus f of 1 all over e minus 1. All right, so f of e, well, that's going to be the natural log of 3e, and then minus the natural log of 3, all over e minus 1. Now, I'm going to use just to simplify this a little bit, I'm going to use a log rule here, because I can split this up as the natural log of 3 plus the natural log of e, which that's going to be 1, okay, then minus the natural log of 3, because if you remember, if we have two things that multiply inside of a natural log, we can split them apart. And now the natural log of 3's will disappear, and the natural log of e is equal to 1. So this actually simplifies nicely down to 1 over e minus 1. Now I'm going to leave it like this for right now. Okay, so the mean value theorem says that there's a point where f prime is equal to 1 over e minus 1. All right, so we're going to find that. We're going to start by finding the derivative. All right, so f prime of x is equal to, well, natural log of 3x will be the derivative of 3x, which is 3 all over 3x. So that's just 1 over x. So there's a point where 1 over x, we're going to set it equal to 1 over e minus 1. And there's a reason why I left it this way, because if 1 over x is equal to 1 over e minus 1, we can just flip both fractions over to get that x is equal to e minus 1. And since e is like 2.7 something, this is like 1.7 something. So that is in the interval 1 to e. Okay, so you could put in the number like in the calculator just to see, or this is good enough. All right, so next up, same problem. Let's see if the mean value theorem applies to x plus 1 over x on the interval 1 to 3. Note, 1 over x would give us problems around 0, but we're away from 0. So f is going to be continuous and differentiable on this interval. Right? So the mean value theorem applies. Okay, so there's a point in 1 to 3 open where f prime is equal to the average rate of change. So let's find that average rate of change. Again, we're doing the same thing over and over again, just with different context. So we're going to have f of 3 minus f of 1 all over 3 minus 1. So f of 3, we'll plug in 3 plus a third, okay, minus, now we're plugging in f of 1. That will be 1 plus 1 over 1, which is 1. Okay, and then we'll have 2 down here. So I get 3 plus a third minus 1 plus 1. So this is a minus 2 here. So this is going to end up being 1 plus a third all over 2. So that's 3 over 3. So that's 4 thirds over 2. Invert and multiply, you'll get 4 thirds times a half. So you'll get 2 thirds. All right, so there's a point in 1,3 where f prime is equal to 2 thirds. Let's see where that is. All right, so we're going to find f prime of x, which will be 1. And then the derivative of 1 over x is negative 1 over x squared. Okay, and so now we're going to set that equal to 2 thirds. All right, now this equation, it may seem tough, but so the best way to start here is just multiply everything by all the denominators we see. So I'm going to take the 3 and the x squared and just multiply by 3x squared. Okay, and by that I mean multiply, not x. Okay, because what you're going to get is a 1 times 3x squared, so 3x squared, minus the 1 over x squared times 3x squared. Well, here the x squareds cancel, and then here we'll have 2 thirds times 3x squared. So here the 3's cancel. All right, so now our equation becomes 3x squared. Here it's just minus 3 is equal to 2x squared. All right, so now we can just move things around. I'm going to move the 2x squared over here and the 3 over here. So we'll get x squared is equal to 3. So x is equal to plus or minus the square root of 3. Now, we are only going to take the plus because that's the one that is in the interval. So the x equals root 3 is in 1 to 3 open, and there we go. There's that point that is guaranteed to exist by the mean value theorem. All right, let's look at a different function. Let's say f of x is equal to 2x to the 1/3 on negative 8 to 8, and we want to know if the mean value theorem applies, and then find the points guaranteed to exist, etc., etc. Now, x to the 1/3. I know that's continuous on this interval because we have an odd denominator for our power here, but I'm not convinced it's differentiable. In fact, if I take the derivative here, you'll get 2 thirds x to the negative 2 thirds, which is 2 thirds times 1 over x to the 2 thirds, and this is undefined when x is equal to 0. Okay, so that means f is not differentiable at 0, which is in this interval, so the mean value theorem is not going to apply. Okay, so we can move on. That's all there is to it. Okay, next up, let's let f of x equal x over x plus 2 on negative 1 to 2. Now, we are dividing here. However, it's negative 2 that would cause this to be undefined. So only x equals negative 2 would cause problems. Okay, so that means f is going to be continuous and differentiable on these intervals here. So the mean value theorem applies. So we want to find the point where that will exist. So I'm going to start by looking at the average rate of change from negative 1 to 2. Okay, so remember that's f of 2 minus f of negative 1 all over 2 minus a negative 1. All right, so f of 2, well, that's going to be 2 over 2 plus 2. All right, so that's f of 2 minus f of negative 1. So that's going to be negative 1 over negative 1 plus 2. All right, all over 2 minus a negative 1 will be 3. All right, this looks kind of gross, but it should simplify a little bit because this is 2/4, so that's 1/2. Okay, minus negative 1 over 1. So that's 1/2 minus a -1 all over 3. All right, so it's actually 1/2 plus 1 over 3. So that'll be 3/2 over 3. And when you invert and multiply, that's 3/2 times 1/3. So it will just be 1/2. Okay, so we want to find where the derivative is equal to 1/2. All right, so let's find the derivative. Unfortunately here, we have to use the quotient rule because we have x over x plus 2. So it'll be the derivative of the top, which is 1, times the bottom left alone, okay, minus the top left alone, times the derivative of the bottom, which is thankfully just 1, all over the bottom squared. So, squared. So what we have up here is x plus 2 minus x all over x plus 2 squared. So the x's cancel up top, and that leaves us with 2 over x plus 2 squared. And we're going to set that equal to 1/2. Now there's a lot of ways we could solve this, but if we want this to be 1/2, that basically means we want the denominator to be 4. I mean, there's a lot of ways we could do this. You could just cross multiply to get that x plus 2 squared is equal to 4. Now, you could multiply this all out, but here's the trick I would suggest. Since you have stuff squared is equal to 4, that means that stuff, x plus 2, is equal to plus or minus 2. Okay, and so x is equal to 2 plus or minus 2. So x is either equal to 4 or 0. Now, we're on the interval, if we remember, -1 to 2. So the 4 is not what we're going to be looking at, but x equals 0 is. So x equals 0 is in -1 to 2. Just double checking. Yes, that is the interval we're looking for. And there we go. There is the point guaranteed to exist by the mean value theorem. All right, since I haven't done it yet, I did want to show on an actual graph here. Here's the graph of the function we just looked at on the interval that we were looking at, right? -1 to 2 of our f of x, the x over x plus 2. Now here's the average rate of change, or at least the line that gives us the average rate of change. Okay, and then if we look at the tangent line at 0, we see that it's parallel to the average rate of change. Okay, so that does actually line up with what we found analytically using the mean value theorem. All right, to round this off, I want to show an example that has actually been used in real life, as far as I understand. And that comes to this situation here. So let's say that a state patrol officer saw a car start from a rest at a highway on-ramp. So he sees the car get on the on-ramp and starting from a very slow speed, and they radioed ahead to another officer that's 30 miles along the highway. Okay. Now when the car reached the location of the second officer 20 minutes later, it was clocked going 60 miles an hour. Now, here's the rub. The driver was given a ticket for exceeding the 60 mile per hour speed limit. Why can the officer conclude that the driver exceeded the speed limit? That may seem kind of crazy, right? Because, well, he wasn't speeding when he or she wasn't speeding when they got on the highway, and they were only clocked going 60 miles an hour, so they were going the speed limit. And it has to do with the mean value theorem. The distance the car travels is a continuous and differentiable function. Okay? Because the distance being traveled in your car is not going to make any jumps. It's not really going to have spikes unless you hit something. the most part, it's going to be a nice smooth function. Okay? All right, so the distance the car travels is continuous and differentiable over time. So if we let, say, d of t be that function, right, then we know that, say, d of 0, let's say, is 0 miles. Okay, and then we can also say that in 28 minutes, so say we're looking at t is in minutes, let's say, but it doesn't matter. We don't have to do it that way, but I'm going to real quick. In 28 minutes, the distance the car has traveled from time equals 0, which we are assuming is when they get on the highway. So let me write that. T equals 0 is when they get on the highway. Okay, so 28 minutes later, they had traveled 30 miles. Right, the distance they had traveled. Now notice, I'm not putting in the 60 miles per hour. That is the velocity. Okay, but what we know is that they have traveled 30 miles, okay, in 28 minutes. So the average rate of change, right, over the interval 0 to 28 is going to be d of 28 minus d of 0 all over 28 minus 0. Well, that's going to be, well, d of 28 is 30 miles. And I'm going to switch back to a different color here. It'll be 30 miles minus 0 miles all over 28 minutes. Okay, so that is 30 miles over 28 minutes. I want to turn that into miles per hour. So to get that in miles per hour, I need to cancel out the minutes. So there's 60 minutes for each hour. Right, so here the minutes will cancel. And so I'll have 30 times 60 over 28, which comes out to be about 64.29 miles per hour. Now, that means by the mean value theorem, okay, so by the mean value theorem, there must be a point in time where d prime is equal to 64.29. In other words, there must be a time where the driver hit 64.2 miles per hour, possibly even higher, but we know for a fact that at least at one time, if not multiple times, the driver hit and exceeded the speed limit. Okay, so yeah, it might be a little harsh to give someone a ticket for going 4 over. However, the proof is in the fact that they traveled 30 miles in 28 minutes. Okay, so it's my understanding that this has actually been used in court before. Okay, that the logical argument using the mean value theorem has held up. Now that might be a myth, but this is what I think is fascinating about the mean value theorem, is that we can actually prove that someone was speeding. Even if they weren't caught at the moment they were, you can prove that they were. Okay? A very interesting logical argument here. And with that, I think I'm going to go ahead and close up this video, and I will catch you all on the next one. Cheers!